Welcome to the lesson on the operation of an electric motor within a battery electric vehicle. In this lesson, we will explore the exciting world of electric motors inside battery electric vehicles and find out how they turn electrical energy into mechanical energy, including the role of electromagnetic forces. We will also discuss the mechanisms of torque and speed control and explain how power electronics and software play a big part in making sure the vehicle performs at its best. Last but not least, we will explore regenerative braking, a technology that helps battery electric vehicles be more efficient and recover energy while slowing down. By the end, we will discuss how regenerative braking makes these vehicles greener and cheaper in the long run. Let us begin by discussing the working of electric motors in BEVs. Electric motors are the key components responsible for converting the electrical energy stored in a battery electric vehicle's battery pack into the mechanical rotational energy needed to drive the wheels. These motors operate based on the principle of electromagnetic induction, which describes the interaction between magnetic fields and current-carrying conductors. At the core of an electric motor are two main parts: the stator, which is the stationary outer part, and the rotor, which is the inner rotating part. The fundamental mechanism lies in the relationship between these parts and the electromagnetic forces generated. These parts, including the controls, cooling mechanism, and other mechanical parts, are packaged in a housing as depicted in the image. The stator is the stationary outer part of the electric motor that houses the windings or electromagnets arranged circumferentially around the rotor as shown in the image. These windings are made of coiled insulated copper wire. When an electric current from the battery pack flows through these stator windings, it creates an electromagnetic field around each winding. By energizing the windings in a specific rotating sequence using a motor controller, the electromagnetic fields produced by the individual windings combine and rotate together, effectively generating a rotating magnetic field around the rotor. The motor controller precisely controls this winding sequence and energization to produce the desired rotating stator magnetic field pattern and strength needed to drive the rotor spin and generate the mechanical output. At the center of the electric motor is the rotor, which is the inner rotating part. The rotor contains an array of permanent magnets or electromagnets arranged around its circumference. As the rotating magnetic field produced by the energized stator windings interacts with the rotor's magnetic fields, electromagnetic forces come into play. These forces act on the rotor magnets, creating a rotational torque or twisting force that causes the rotor to spin. The direction of the electromagnetic force acting on the rotor conductors is determined by Fleming's left-hand rule, which states that if you point the thumb of your left hand in the direction of the current flow and your fingers wrap in the direction of the magnetic field lines, your palm will face the direction of the resultant force. This torque-producing rotational force keeps acting on the rotor as long as current flows in the stator, enabling continuous spin to generate mechanical rotational energy output. The intensity of the electromagnetic forces, and hence the torque, depends on the strength of the stator's rotating magnetic field, which is controlled by the amount of current supplied. The rotating magnetic field of the stator constantly changes the direction of each rotor magnet's magnetic field. This changing magnetic field induces a tangential force on the rotor magnets according to the laws of electromagnetic induction. This tangential force acts like a continuous twisting force, causing the rotor to spin in order to continuously catch up with the rotating stator magnetic field. The rotor is mechanically coupled to a shaft running through the center of the motor. This allows the rotational motion of the rotor to be transmitted to the drive shaft, which is further connected through a gearbox or direct drive mechanism to the axle or the wheels of the vehicle. In this way, the electromagnetic rotational forces on the rotor are ultimately converted into rotational torque to propel the vehicle's wheels and provide motive force. Let us now understand the mechanisms of torque and speed control in BEV motors, including the roles of power electronics and software. Electric motors in battery electric vehicles are not just responsible for converting electrical energy into mechanical motion, but also require sophisticated control systems to precisely regulate their torque and speed outputs. Efficient operation of the vehicle depends on the ability to accurately control these two key parameters of the motor. Torque control is critical for enabling desired acceleration performance from the vehicle, as higher torque translates into greater rotational force to spin the wheels faster. It is also essential for hill climbing ability when the vehicle needs to overcome increased load forces. On the other hand, speed control of the motor is important for maintaining the desired vehicle speed, whether cruising on the highway or navigating urban speeds. Without refined speed control, the vehicle would be unable to hold a steady speed. Both torque and speed control work in unison to deliver a smooth, controllable driving experience while maximizing the efficiency of the electric motor's operation over varying driving conditions. It is important to note that the direction of current applied to the motor determines whether the vehicle moves forward or backward. The ability to precisely control the torque and speed of the electric motor lies in the power electronic systems that interface the battery pack with the motor itself. At the heart of this is the inverter, which acts as the critical link between the DC power from the battery and the AC power required to drive the motor. The inverter takes the DC voltage from the battery pack and converts it into an AC voltage. This AC voltage is then supplied to the motor windings. However, simply providing AC voltage is not enough for torque and speed control. The inverter employs pulse width modulation, abbreviated as PWM, to vary the effective voltage and current being delivered to the motor windings. By adjusting the width of the voltage pulses, PWM can increase or decrease the average voltage and current supplied. Higher voltage and current result in a stronger electromagnetic field, producing higher torque from the motor. Conversely, lower voltage and current reduce the torque output. This PWM modulation allows the inverter to precisely regulate the torque by controlling the voltage and current reaching the motor windings. While power electronics like the inverter provide the hardware capability to control the motor's torque and speed, the intelligence behind this precise control lies in the motor control software programmed into the vehicle control unit, abbreviated as VCU, the brain of the vehicle's electronics. This sophisticated software continuously monitors and interprets driver inputs such as the accelerator pedal position, brake pedal, and gear selection, namely park, drive, neutral, and reverse. Based on the inputs and predefined control algorithms, it calculates the desired torque and speed set points that the motor needs to achieve for optimal performance and efficiency. The software then sends finely tuned control signals to the power electronic systems, instructing them on how to modulate the voltage and current supplied to the motor windings. This could involve techniques like adjusting the PWM duty cycle of the inverter or varying the input frequency to control torque and speed respectively. The motor control software acts as the bridge between driver inputs and the power electronics hardware, translating driving needs into precise electrical control over the motor's mechanical output in real time. When it comes to torque control strategies for electric motors and battery electric vehicles, two prominent techniques are field-oriented control, abbreviated as FOC, and direct torque control, abbreviated as DTC. The FOC is a more complex approach that separates the control of the magnetic flux and motor torque, enabling highly precise and accurate control over the motor's operation. It requires detailed mathematical modeling to continuously align the stator's magnetic field with the rotor, maximizing torque output. While FOC offers exceptional high-performance capabilities, it comes at the cost of increased computational complexity and the need for additional sensors. In contrast, direct torque control is a more straightforward strategy that directly controls the motor's torque output and stator flux, without requiring an explicit motor model. It uses simpler and more cost-effective computations, though with slightly less precision compared to FOC. As a result, FOC is often the preferred choice for high-end BEV applications demanding superior dynamic performance, while direct torque control finds its spot in cost-sensitive applications or scenarios where sensor-less control is required. For speed control strategies, one of the primary methods for controlling the speed of an electric motor is through a variable frequency drive, abbreviated as VFD. A VFD works by adjusting the frequency of the AC voltage supplied to the motor windings. There is a direct relationship between this input frequency and the motor's rotational speed. A higher frequency results in a higher rotational speed, while a lower frequency leads to a lower speed. By varying the frequency, the VFD can precisely control and maintain the desired motor speed under different operating conditions. However, for applications requiring highly dynamic and accurate speed control, such as traction motors, a more advanced technique called vector control is often employed. Vector control involves continuously monitoring the rotor's rotational position using position sensors or estimation algorithms. This rotor position feedback allows the control system to precisely regulate the phase angle between the stator's rotating magnetic field and the rotor's magnetic field. By continuously adjusting this phase angle, vector control can dynamically govern the motor's speed with exceptional precision, enabling rapid acceleration and deceleration and maintaining a constant speed under varying loads. This level of speed control performance is critical for ensuring a smooth and responsive driving experience in BEVs. Let us move on to the next topic, regenerative braking. This section aims to discuss the principles and benefits of this technology and how it contributes to a BEV's efficiency and energy recuperation. One of the key innovations that contributes to the energy efficiency and extended range of battery electric vehicles is the implementation of regenerative braking systems. Unlike conventional vehicles that waste the kinetic energy of the moving vehicle during braking, regenerative braking allows BEVs to capture and reuse a significant portion of this energy. By reusing this energy instead of wasting it, regenerative braking significantly improves the overall energy efficiency of the vehicle and allows it to travel further on a single battery charge, improving its driving range. The fundamental principle behind regenerative braking lies in the ability of an electric motor to act as an electrical generator during braking or deceleration when the vehicle's wheels drive the rotor. During braking events in a BEV, the still spinning wheels driven by the vehicle's inertia force the motor's rotor to spin. However, instead of allowing this rotation to simply slow down due to friction, the motor's stator windings are reconfigured by the control system to operate in generator mode. As the rotor spins within the stator's magnetic field, it induces a flow of electrical current in the windings, effectively converting the vehicle's kinetic energy into electrical energy. Simultaneously, this generator action also applies an opposing torque force on the rotor shaft, which translates to a braking force on the wheels, slowing down the vehicle's motion. The electrical energy generated is in the form of AC power, which is then fed through an inverter to convert it into DC power compatible with the battery pack. This recovered DC power charges the battery, allowing the kinetic energy that would have been wasted during friction braking to be captured and stored for future use, thereby increasing the vehicle's overall energy efficiency and driving range capability. Regenerative braking offers several significant benefits that contribute to the overall efficiency, performance, and driving experience of battery electric vehicles. Firstly, by recovering a portion of the vehicle's kinetic energy during braking and converting it into electrical energy to recharge the battery, regenerative braking improves the vehicle's energy efficiency. This captured energy would otherwise be wasted as heat through conventional friction braking. As a result, regenerative braking effectively extends the driving range that can be achieved on a single battery charge. Moreover, since regenerative braking relies on the motor's generator action to apply a braking force, it reduces the workload and wear on the vehicle's conventional friction brake pads and discs. This leads to extended service life for the friction brakes and lower maintenance costs over the vehicle's lifespan. Additionally, the blending of regenerative and friction braking forces provides a smoother, more linear braking feel compared to purely friction-based systems. This enhances the driving experience and makes it easier for drivers to modulate braking inputs precisely. Let us now summarize the key points we covered in this lesson. Electric motors in battery electric vehicles convert electrical energy from the battery into mechanical rotational energy, which drives the wheels. These motors operate on the principle of electromagnetic induction between the stator and rotor. The vehicle control unit, utilizing power electronics and motor control software, achieves precise torque and speed control. Variable frequency drives and vector control methods are employed to manage speed control effectively. Additionally, regenerative braking systems enable the motor to function as a generator during braking, recovering kinetic energy and recharging the battery in the process. The combination of advanced motor control, power electronics, and regenerative braking systems contributes significantly to the overall efficiency and performance of BEVs. Thank you.